Okay, moving on to page 6 of the 0.2 Algebra 2 review packet, we're going to look at the topic of inverse functions. So this page says to determine the inverse of each function, state the domain of the function and its inverse. So quickly to recap inverse functions. Okay, so a function's inverse basically undoes what the function did. So if f of x equals something, let's call it x plus 2, right? That means we take our x input and we just add 2 to it, and we get f of x. So we get some input, some output. So negative 2 would be 0, negative 1 would be 1, so on, so forth. Okay, now the inverse function takes that and it just undoes everything. So f inverse x, instead of adding 2, to undo that, we would have to take some input and subtract 2. Okay, so when we plug in something to our inverse function, such as 0, and subtract 2, we get negative 2. 1, we get negative 1. 2, 0. 3, 1, 4, 2. And that's f inverse x. And so the inverse function has the feature of taking the outputs of the original function and mapping them back to the inputs. So it tells you what did we put in, right, to get out this output. So we have input and we have output, and then this takes your original output of f of x, and it ends up being the input of f inverse x, and it tells us the original input of f of x that produced that output. Okay, and that ends up being our output of f inverse x. So it has the feature of swapping the inputs and outputs. Swap inputs, outputs. Okay, it allows us to know how we got that output. And so the domain of f of x, right, our inputs of f of x, end up being the range of f inverse of x. Okay, and the range of f of x is the domain of f inverse x. So the things that we got out of our original function end up being the things we can put in to our inverse function. So that's this interrelationship. And for a function to have an inverse, it needs to be a 1-to-1 function. Okay, so each input produces a unique output. Okay, because to be able to invert it and still be a function, that needs to be a case. And we'll see what happens with this in a minute. So the process for actually finding the inverse function, algebraically, typically we just switch x and y and solve for y. So here we would say x is equal to 2/3 y minus 3 plus 4. I'm going to start by subtracting 4, so x minus 4, then multiplying by 3/2 equals y minus 3. Then I'll add 3 to both sides. So 3/2. You don't have to distribute. You could. I won't for a second, so we get 3/2 x minus 4 plus 3 equals y. But remember, we're looking for f inverse x. So at the end of the day, we replace it. Y is just sort of easier to write in the meantime. So that's great, and if I wanted to distribute in, I could, but I'm not going to. And the domain of both functions, domain of f of x is all real numbers, domain of f inverse x is all real numbers. Both of these are just linear functions because the domain and range of both is all real numbers. So if you switch domain and range, it's still the same thing. One thing to sort of pay attention to, though, to quickly check if you've done your inverse right, the inside, this minus 3, switches to plus 3 on the outside. the plus 4 on the outside switches to minus 4 on the inside, and then times 2/3 on the outside should switch to times 3/2 on the inside. Which it kind of would if we were to actually distribute everything out. Yeah, so we should be pretty happy that this is in fact our inverse function. Okay, on the next example, we're going to run into a problem. So g of x is a quadratic, and a quadratic is not a 1-to-1 function, okay? If I look at a quadratic and I have x and I have f of x, or x squared, -2, -1, 0, 1, 2 produces 4, 1, 0, 1, 4. And so we can see that I get repeated outputs. Like I get a 4 from -2, I get a 4 from +2. So if I wanted to have some inverse function, x and f inverse x, and I wanted to know, well, for my output of 4 over here, what was my input? Well, I don't know. It would have to be both -2 and 2. But that's not a function, right? We can't have some input produce two different outputs. So that's not a function, and that's the case with 1. That could have come from -1 or 1. And then 0 is the one exception, the vertex. That's okay. But that's a problem. So this is not a 1-to-1 function. We cannot take the inverse of this function without restricting the domain. So if we cut our domain and we said, let's just take a slice of this function, like say cut it at the vertex, and I just take this positive half of the function, then we could invert it, because then we would only be looking at these values. Or you could instead choose the left half of the function, the negatives, and still invert it. But you can only invert this function if you restrict the domain, okay? Would need to restrict domain. And I want to show that. So if we have this function, let's come down here. I'm going to add another page. Okay. What was our function? -3x + 2 squared. And was it +5? -5. -5. And let's call that f of x, right? Okay, and so this function, right, we said at the moment we have, if we were to graph this, x + 2, so that shifts us left 2 down 5, so our vertex would be at -2, -5, and then -3 means our function's facing downwards. So here it goes, okay, and then I have some set of axes, I don't know. Something like this, right? And that's not the most accurate picture in the world, but it's okay. And so we said we could either take the right half of our function, or we could take the left half of our function. You could do one or the other, but otherwise we can't. So if I look at a table of values for f of x, I could say x, f of x, and let's just do... So -2 is our vertex. So I'm going to start at -2, -3, -4, -1, 0. And our outputs, if we put these things through our function, if I put in -4, plus 2 is -2, squared is 4, -12, so I should get -17. -2 is our vertex, so we should be getting -5. Put in -3, we get -1 squared is +1, -3 minus 5, -8. And then by symmetry, we should expect to get the same things on these points, right? So if we think about it, our green half of the function would be right here. That's the left side of this function. And the right side of the function is here. And they sort of share this vertex point, because we could include the vertex in either one. And so those are two domains. That's the domain of x is less than or equal to -2, and we have a domain of x is greater than or equal to -2. So those are the two ways we could restrict our domain to make this one-to-one and then not have copies of our function. So I'm going to show both. If we said we have f of x equals -3 x plus 2 squared minus 5, and let's do the positive domain where x is greater than or equal to -2, I'm going to go ahead and solve this. So I'm going to switch x and y. X equals -3, y plus 2 squared minus 5. We'll get x plus 5 divided by -3. Okay. And then we'll end up with y plus 2 squared. Now remember, when you take the square root in the process of solving, we need plus or minus the square root of -x plus 5 over 3. And then equals y plus 2, so then we'll eventually subtract 2 and get f inverse x. But there's a problem, because at the moment we have plus or minus, right? That's two things. So if we look back to this original domain, that's saying we had this part of the parabola, right? We took that part of the parabola. And that's going to correspond to our positive version of our square root. So if we take that parabola and we imagine turning it sideways for our inverse, right, we would have some positive, if it's -2, -5, it would be -5, -2. So it'd be some here, we'd have a positive piece and a negative piece. And the positive piece corresponds to the positive half of the domain, the negative piece corresponds to the negative half. So my actual f inverse is going to be positive square root of -x plus 5 all over 3 minus 2. Okay. On the other hand, if instead we had f of x equals -3 x plus 2 squared minus 5 with the domain restriction x is less than or equal to -2, basically all the math would be the same, but when we get to this plus or minus square root of -x plus 5 over 3 minus 2 is f inverse x. Again, that's describing both of these failing the vertical line test, which is a problem. It's got the plus root, right? Here's the positive root, and here's the negative root. And so because we're to the left of the parabola, that's going to correspond to the negative part of the roots here. And so we will say negative square root of -x plus 5 over 3 minus 2 is f inverse x. Okay, and that is sort of the gist of things. It's a pretty quick explanation. I mean, I tried to hit on some key points, but it does rely on sort of having learned this before. And if you still have questions, as is very common with this one, I highly recommend finding a teacher, find me, and ask about it. I can explain it a little bit more in detail. But this is supposed to be a little bit of a refresher that hopefully jogs your memory of why do we have to restrict the domain, where would we restrict it, and how does that actually play out in our inverses. So we choose to restrict it at the inverse, or at the vertex, sorry, and then that affects whether we take the positive or negative root eventually. Okay, so coming back to these inverse functions, the rest of them probably won't be quite so complicated. So if we have square root function, okay, well actually the square root function, when we do the algebra, let's see what happens. And let's go for blue. So we get x equals square root of 2x plus 1 minus 3. And now we want to make a note, the square root function looks a little something like this when it's a positive root. And so I'll solve for, oops, I always do that. This should be y. I'll solve for y. So I'll do x plus 3 equals square root of 2y plus 1. I'm going to square both sides. X plus 3 squared equals 2y plus 1. Subtract 1, x plus 3 squared minus 1, and then divide 2. Okay, equals y, or f inverse x. But there's a problem, because while this looks okay, right, inside out, outside in, and what I mean by that is the minus 3 outside becomes plus 3 inside, plus 1 inside becomes minus 1 outside, times 2 inside, divide by 2 outside. So we're pretty happy with things. but this is currently describing a parabola that would look a little something, and I don't know exactly where it is, but it would look a little something like this. And you can kind of see those realistically aren't inverses of each other. We need to cut our parabola and actually only take this half of it, because those will be the inverse parts. And so we're going to restrict the domain of our parabola to only be the positive side. So x is greater than or equal to, and I'm going to use the x coordinate of the vertex, which is -3, and that's going to get me my correct domain restriction. Okay, so something to keep in mind with these even powers, quadratics, fourth power, and then their inverse, the square roots or fourth roots or whatever, it's pretty important to think about these things. Our next one, we have -x cubed minus 1. We should be okay to invert this. So we should say x equals -y cubed minus 1. The domain is all real numbers, the range is all real numbers, and this is at the moment a one-to-one function. So we would get x plus 1, divide by -1, so I'll just throw a negative out here, equals y cubed. So then we would get cube root of -x minus 1 equals fj inverse x. And we'd be all very happy. So now we're supposed to be stating the domain of the original function and its inverse. So our original domain of f of x was all real numbers. Domain of f inverse x is also all real numbers. Okay, that's just how cubics and cube roots go. This one, our domain of f of x was -1/2 to infinity. -1/2, comma infinity, and of f inverse x would be -3, comma infinity, because we have to take that part. And that was the original range of f of x. Great. All right, on to an exponential function. So we have 3 times e to the power of x. So the domain of that is all real numbers. The range of that is from 0 to infinity. So I'll just write that. Domain, all real numbers, range 0 to infinity. Okay, this is an exponential function. It has an asymptote at y equals 0 by default. Switching x and y, we'll get x equals 3 times e to the y, divide by 3. X over 3 is equal to e to the y. To get the y out of the power, we need to take log base e of both sides, which you might know as natural log. So I'll take log base e of x over 3 equals log base e of e to the y. And we will get log base e, or ln, x over 3 equals k inverse x. Okay, and the domain of k inverse x is going to be from 0. Right, we can put in 0 to our log function, and we can put in all the way to infinity, but we can't take negative inputs in our logs. We also can't actually take 0. I put this curly bracket for 0 because logs are undefined for 0. Okay, moving on. Domain of this log function, domain by default is 0 to infinity for logs. I'll throw down the range is going to be all real numbers. And so, again, and I should have pointed this out last time, the range of this function corresponds to the domain of its inverse. And that always just seems to happen. So if we move right along, let's change the color for some contrast. Go green. So if I switch x and y, x equals 3 log x minus 4. I always do this. 3 log y minus 4. X plus 4 over 3 equals log. And though log is log base 10 of y. So exponentiating, we're going to get 10 to the power of x plus 4 over 3 equals y, which is m inverse x. Which is great, and then the domain of an exponential is all real numbers. And we will note that this range and this domain match, which with an inverse function should be the case. So things with inverse functions, switch x and y solve for it because we are basically taking all the inputs and outputs and interchanging them. The domain of an original function becomes the range of its inverse and vice versa. And then if it's not a one-to-one function, such as a parabola, absolute value, or anything along those lines, you have to restrict the domain of the function to be able to invert that. So that's a really key idea. It's a tricky one, but that's something that's really important. So try to take the time to figure that out, feel really solid about this. Again, this is kind of a quick review because I'm assuming we've seen this all already, but